Hello guys, welcome back to the video again. In this video we will discuss Oof. In this video we will discuss some more things. Alright. Alright guys. So we were discussing eigenvalues and eigenvectors. So let's continue here. We have given Ax is equal to uh, how to approach eigenvalue eigenvectors. Alright. So we know eigenvalue eigenvector cannot be zero. Alright. Eigenvalue can be zero. And so eigen this is a vector, all right. So by multiplying by multiplying any matrix to the vector, if the vector does not change its direction, it just change its magnitude, all right. So let's say magnitude of this vector change by lambda times, or lambda times of x. So this is the way, all right. So what we can do, ax minus lambda x is equal to 0, which goes like a minus lambda I x is equal to 0, like that, right. What we are saying, x can't be 0, x can't be 0, right. Then what, magnitude of a minus lambda I should be 0. If a minus lambda I uh, determinant of this is 0, then what, then we are saying that columns of a minus lambda I are linearly dependent, or we can say rank, we can say let's say rank of a minus lambda I is less than n, right. So means it always has free variables, right. So by solving this we can do like a minus lambda I is equal to 0. So then we solve this and we find the roots. This is step 1. Step 2, what we find, we find roots of the polynomial. We get the polynomial from this, and in terms of lambda, we find roots for lambda. All right. The roots are, then we get n values of lambda which are roots. This is called eigenvalues. Eigenvalues, all right. And when we put the eigenvalues one by one, we get n eigenvalue. We put these eigenvalues one by one in this equation, all right, or we can say in this equation, and we solve. We get the values of we get eigenvectors. Then ax, we get then bx is equal to 0. Solve this, then get eigenvectors. Eigenvectors, right. Right. So next thing is, what is geometric multiplicity? So geometric multiplicity is, for a particular eigenvalue, we solve, we get the what we say, for the particular eigenvalue, We get a matrix. Alright, we solve this. We get eigenvectors. From those eigenvectors, we have some linearly independent eigenvectors, or we can say linearly independent solutions. Alright. So number of linearly independent solutions is the geometric multiplicity corresponding to lambda. That lambda. Right? What is arithmetic multiplicity? Arithmetic multiplicity is number of times lambda is repeating. Right? Number of times lambda is repeating. This is called arithmetic multiplicity. Geometric multiplicity is always less than arithmetic multiplicity. So we can search for this also, that geometric multiplicity, number of linearly independent eigen vectors corresponding to eigen value. Eigen value, and we know that arithmetic multiplicity number of times particular value is repeating. Alright. So yeah, this is correct. If let's say a lambda value eigenvalue is 2. So for 2, let's say 2 repeats 3 times. Alright. So there is a possibility that for corresponding to eigenvalue 2, we can get 3 linearly independent solutions. Alright. Or we can say eigenvectors. But if any eigenvalue only repeats one time, right, unique, then it can only have at most one linearly independent solution corresponding to that. Alright, at most one. This is called, then in this case arithmetic multiplicity is called to geometric multiplicity. So algebraic multiplicity or algebraic, what the hell? Is the eigenvalue is lambda is the number of times it appears as a root of the characteristic polynomial of the matrix. In similar terms, is the power of which the factor. Yeah, factor appears as the factor root. Eigenvalue lambda is the dimension of the eigenvector. All right. The number of linearly independent things. This determines the dimension of the eigenspace. All right. So geometric multiplicity determines the dimension of the space. The eigen space is the null space kernel of the matrix. Where is the origin is the quadratic matrix in the words the number of linear independent eigenvectors associated with eigenvalue. All right. Where is one? A matrix is diagonalizable if and only if it for every eigenvalue. The geometric multiplicity equals the algebraic multiplicity. If even one eigenvalue has geometric multiplicity less than the algebraic multiplicity, the matrix is not diagonalizable. All right. Right. So this is a note. A matrix is you understand this is a diagonalizable realizable if and only if geometric multiplicity is equal to arithmetic multiplicity. Arithmetic, right? This is even if one eigenvalue has the dimension of eigen space, dimension is of eigenspace. Understanding eigenstructure. The multiplicities give you a more complete picture of eigenstructure of a matrix than just the eigenvalues themselves. They tell you about the number of independent eigenvectors you can find for each eigenvalue and how that relates to the eigenvalue rule to the hell. What? Second thing, the multiplicities give you the more complete picture of eigenstructure of a matrix than just the eigenvalues themselves. Right. They tell you about the number of independent eigenvectors you can find for each eigenvalue and their how it relates to eigenvalue in the rule of areas. Application of differential equation and linear system. Eigenvalues and eigenvectors are fundamental to solving systems of linear differential equations, realizing the stability of system and understanding long-term behavior of linear models in various fields like physics, engineering, and economics. All right, like this. And another thing, guys, is let's start this. Another thing is let A is 5 cross 5 matrix. All right. Rank of A minus lambda 1 I is 2. Then what? We have three free variables. If we have, let's say, one more thing. A matrix is 5 cross 5 matrix. All right. And A minus lambda 1 I has rank is equal to 2. Which means what? It has two linearly independent vectors. No, three free variables. Which means what? It has three linearly independent solutions, or we can say eigen vectors. Three linearly independent eigenvectors. Is this true? So it has a geometric multiplicity of 3. Alright. This is the true. Alright. Let's say we have a determinant of a product of eigenvalues. We know that determinant of A of a matrix is the product of eigenvalues of that matrix. This is true. If columns of A are linearly dependent, if columns of A any matrix is linearly dependent, then the determinant should be 0. Alright. Hence, one of eigenvalues must be 0. So, one of eigenvalues also 0 because we have lambda 1, lambda 2, dot, lambda n equal to determinant of A. If it is 0, then one of the eigenvalue must be 0 here. Alright. If eigenvalues of A is not equal to 0, so any eigenvalue is not equal to 0, then determinant is not equal to 0 also. Determinant is not 0 means all the columns of a matrix are linearly independent and rank is is equal to n. Rank of A is equal to n. These are all under related things. Right? If eigenvalues of A is any matrix A, then rank of A, let's say if there is an eigenvalue which is 0, alright, then determinant is 0. If determinant is 0, then rank should be less than n. At least one free variable. These are all interrelated things, all right? Very important. It can be asked in any question, examination. This is very helpful also. A minus lambda I x. Let's say we have a minus lambda I x is equal to 0. Irrespective of values of lambda, then there is always at least one free variable. A minus lambda x is equal to 0. All right. Let's say irrespective of values of lambda, there is always at least one free variable. All right, yeah. There is always in value many solutions and eigenvalues. Right, eigenvectors. If lambda is equal to 0, there will be at least one free variable. Because determinant is 0 and determinant is 0 less than a. For lambda is equal to 0, a minus lambda x is equal to ax to 0. Then number of linearly independent vectors equal to nullity equal to number of free variables. Alright. So let's say we have something. Let's say we have a matrix. Alright. We have a matrix of 5 cross 5. Alright. And it has four linearly independent eigen vectors. Right? What is the rank of A? Rank of A. So eigenvectors are the solutions. All right. So we have the four linearly independent solutions. But what is if it has rank 4? If it has 4 free variable, we can say. If it has 5 free variable, we can say. All right. So we can say if it has uh, 4 or 5, we can't say anything. Can't say anything about rank here. All right. Yes, because there is no information about whether there is a four linear independent vector corresponding to lambda is equal to 0 or whether there is any lambda is equal to 0 or not. Right. So, so let's say for this question only, we ask this question to ChatGPT or anything. Let A be 5 cross 5 matrix and it has four linear independent eigen vectors. What can we say what can we say about rank of A? Alright, what can we say about rank of A? Rank nullity for any matrix A, the rank of A is precisely nullity of A equals to number of columns of A. In this case, rank plus nullity equal to 5. Nullity of n eigenvalues. The nullity of A minus lambda I is a dimension of the eigenspace. Alright, because nullity means nullity. What nullity defines? Nullity defines number of linearly independent solutions. Number of linearly independent eigenvectors defines geometric multiplicity, and geometric multiplicity defines what? Eigenspace. All right. Dimension of the eigenspace is the geometric multiplicity of the eigenvalue. All right. Zero equivalence. If zero is an eigenvalue of A, then null space of A. If zero is an eigenvalue of A, all right. Zero is an eigenvalue of A, then null space of A, which is the eigenspace corresponding to eigenvalue 0, has zero dimension, non-zero dimensions. Since there are four linearly independent eigenvectors, case 1, all four eigenvectors correspond to non-zero eigenvalues. This could be the line. In this case, we know that we have at least one more eigenvalue. Is that fifth eigenvalue is 0? Then the dimension of the null space is at least 1. Alright, we have uh, if we have all four eigenvectors correspond to non-zero eigenvalues, then what? Uh, non-zero. In this case, we know that we have at least one more eigenvalue. All right. If the fifth eigenvalue is 0, then the dimension of the null space of A is at least 1. Alright. At most, at least 1, therefore nullity is greater than or equal to 1. Alright. Using the rank nullity theorem, rank is equal to 5 and nullity is equal to 4. If the fifth eigenvalue is non-zero, then matrix is full rank. The nullity is 0. So rank is equal to 5. Alright. One of the four eigenvector corresponds to the eigenvalue 0. If one of the four linear independent eigenvalues 0, then nullity is at least 1. That means rank is less than equal to 4, which we have to note down 4 linear independent eigenvectors cannot be greater than 4. Therefore, rank is greater than equal to 1. So we have to understand this very uh, so based on this, we have to analyze the. Alright, wait a minute. We go for group. चले. Wait a minute. You go deep sea, no? Wait a minute, I will be back. हाँ हाँ। मैं कहाँ से देगा आलू यार, मैं काम कर रहा हूँ तो बताओ, आपको बाल लगे भेज। वो तो बढ़िया, मैं कहाँ जाऊँ, मैं कौन दिखाऊँ। क्या बात है। Okay, let's see. The user is asking for about, let's say, 5 cross 5 matrix. A that has four linearly independent eigenvectors. They want to know that we can say about the rank of A. I need to recall linear algebra concepts here. First, the rank of a matrix is the dimension of its column space. Alright, which is the which is the same as the number of linearly independent columns. But how does that relate to eigenvalues and eigenvectors? Well, eigenvectors correspond to distinct eigenvalues are linearly independent. Alright. If the matrix has four linearly independent eigenvectors, that suggests something about its eigenvalues. But wait, a 5 cross 5 matrix has 5 eigenvalues, counting algebraic multiplicity. If there are four linearly independent eigenvectors, maybe there is a repeated eigenvalues. Maybe there is a repeated eigenvalue. Yes, very good. Wait, the number of linearly independent eigenvectors is related to geometric multiplicity of such eigenvalues. The geometric multiplicity of the dimension of the eigenspace, which is well, the number of linearly independent eigenvectors is related to the what? Wait. The number of linearly independent eigenvectors is related to geometric multiplicity, okay, of each eigenvalue. Alright. Of each eigenvalue corresponding to a eigenvalue. Linearly independent eigenvector related to geometric multiplicity. Alright. The geometric multiplicity is the dimension of the eigenspace. Alright. Which is the number of linearly independent eigenvectors for that eigenvalues. Alright. If the matrix has four linearly independent eigenvectors, maybe one eigenvalue has geometric multiplicity 1 and other contribute the rest. Other contribute the rest. Maybe one eigenvalue has geometric multiplicity 1 and other contribute the rest. Alternatively, maybe there is a defective eigenvalue, meaning its algebraic multiplicity exceeds its geometric multiplicity. For example, if an eigenvalue has algebraic multiplicity 2 but geometric multiplicity 1, then it contributes only one eigenvector. So if the matrix has four linearly independent eigenvectors, perhaps one eigenvalue is defective. But how does that affect the rank? The rank is related to the null space via rank nullity theorem. Rank plus nullity is equal to 5. Nullity is the dimension of the null space, which is geometric multiplicity of the eigenvalue 0. If 0 is an eigenvalue, wait. But if 0 is not eigenvalue, then the null space is a trivial, only the 0 vector. So nullity would be 0 and rank is equal to 5. Nullity is 0 and rank is equal to 5. What? How can this possible? But if 0 is eigenvalue, the nullity geometric multiplicity is of 0. No. This is not correct. Going well. Let's say, but if 0 is not eigenvalue, wait a minute. Nullity is a dimension of the null space, which is geometric multiplicity. Shivam? 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 But how does that affect the rank? The rank is right. The rank right. Nullity is a dimension of the null space, right? Which is geometric multiplicity of the eigenvalue zero. If zero is eigenvalue, alright. If zero is an eigenvalue, let's say, then we have zero is eigenvalue. We have some corresponding eigenvectors also. Right? If zero repeats n times, then we have n zero to n, one to n eigenvectors. Right? So if zero is eigenvalue, then zero is eigenvalue. Wait, what if zero is eigenvalue? Then the null space is trivial. But only if zero vector, only the zero vector. So nullity would be zero. Rank is equal to 5. But if zero is eigenvalue, then nullity is geometric multiplicity of zero. Alright. So if the matrix has four linearly independent eigenvectors, maybe one of them is associated with the eigenvalue zero. Suppose zero is eigenvalue, the geometric multiplicity 1. Since there are four linear independent total, maybe other eigenvalues are distinct with geometric multiplicity 1 each. Then the nullity would be 1. Right? So rank will be 5 minus 1 equal to 4. If 0 is the then x nullity is equal to 1. Why are we equal to 1 then? Right. But wait, if there are four elements, suppose some of them correspond to non-zero eigenvalues. For example, if there are two eigenvalues, one of is absolutely true and one of is one, and other is three, then total eigenvectors will be 4. In this case, the null space, if 0 is not eigenvalue, then it will be 0. The rank would still be 5. What the user did not specify that 0 is an eigenvalue. That's conclusive. Internet will be addition of four eigenvectors implies that the one eigenvalue with geometric multiplicity 1 but not necessarily 0 could vary on less. It's a long discussion, we can't try that. So we will skip here. It's very hard and time consuming here. Alright, let's say we have a matrix A B cross A n cross n and B n cross n. Then AB is equal to BA does not hold, alright? But AB trace of AB is equal to trace of BA, alright? Then we say AB and BA share non-zero eigenvalues. Share non-zero eigenvalues, alright? If A n cross n has eigenvalues lambda 1, lambda 3, and n, this is very important. Why is this true? Because trace of a matrix is equal to sum of eigenvalues. Is this true? Yes, you are correct. Trace of a matrix is indeed equal to sum of eigenvalues. Let's dive there. All right. I'm not hearing. Trace of A is equal to sum of eigenvalues of A. So the Bayesian on the eigenvector. Right. Is very important also. So let's say we have given some. We have given some. This is a given matrix. Then what is the trace of A? Trace of A is equal to 2 plus 3 plus 4 equal to 9, and then sum of eigenvalues equal to 9 also. Right. Give me another example. For any square matrix. For any square matrix, this is true. For any square matrix, this is true. All right. Then we discuss that if a matrix A enclosed and has eigenvalues, let's say lambda 1, lambda 2, then what is the A plus I? I means what? We just adding what is eigenvalues A plus I, then lambda 1 plus 1, lambda 2 plus 2, like that. We are adding the I, diagonal matrix. For matrix which just rotate the vector. So one more thing here. Any matrix which just rotate the vector, change the direction, then it does not have any eigenvalue in eigenvectors. It does not have any eigenvalue in eigenvector because it's not it is not increasing or decreasing the magnitude of the vector, just rotating it. Ax is equal to lambda x. Let's say is lambda is eigenvalue. Right. What is this theory here? That this theory is if ax is equal to uh, kx, k is value, then if kx dash is equal to k dash x dash, then k dash also a equal value. Explain this. You are absolutely correct. Let's clarify the formalize the statement. If ax is equal to kx and ax dash is equal to k dash x dash, where A square matrix x is a non-zero eigenvector corresponding to eigenvalue k. X is a non-zero eigenvector corresponding to eigenvalue k dash. It means that k dash is also eigenvalue of A. This is true. Why not? Why not? Eigenvalue of A. Why not? It can be different, no? Yes. If one more thing, let's say we have a matrix A, then is to power k is equal to zero. We get zero matrix. This is called nilpotent matrix. Nilpotent matrix here, right? Then we are discussing LU decomposition here. This is very important. LU decomposition. So how to understand this? Let's say we have given a matrix here, all right? A11, A12, A13, A21, A22, A3, A23, A31, A32, A33. This is a given matrix. We have to divide it into two things. One is L, one is U. All right. L is what? L is lower triangle, lower one, one, and one. Then we have L21, L31, L32. Then all we have zero here. Zero, zero, then zero. This is the matrix here. L. And we have upper matrix U L. U11, U22, U33. These are all zero here, zeros. And U12, U13, U23. This is the upper trend. So this is how value decomposition works. Then we we make them zero first, then corresponding to them change the sign. We change signs here. So should we do that? Should we do that? Yes, we can do. But we can do this. But so take an example. Just take an example. Take example is this. This is the example. Let's say we have a matrix 1, 4, minus 3, minus 2, 8, 5, 3, 4, 7. Alright. This is the LU decomposition. So we put L and U first. So we have L. This is the matrix, alright. This is the matrix. For this, we have one here, and one here, and we have zeros here, right? And this is the L part, lower part, and this we have U part. One, two, three, one, two, three, one, two, three. Okay. So we have to make them zero, and so make changes in this and put those changes. How to make this zero and how to make this zero. So how what is the changes we have to do in this? Is like R2 is equal to R2 plus 2R1. R3 is equal to R3 minus 3R1. This is elementary row operations we are doing. And it goes like this is 1, 4 minus 3. And it comes to 0 here or 0 here. So what is this becoming? Plus 2R1. This is becoming 16 here. And this is becoming or minus 1. Alright, then we are doing this minus 3 r1. So this is 0, minus 3, 4, 3, 12, 30 12, 8 minus 8, and Prantia 9 plus 3, 7 और 9, 9 7, 16. This becomes 16. 16. Then for these parts, what we are doing? We are putting just to change the sign, all right? What we are using the we can say coefficient or a constant. What constant we have used in these just to make this zero and to make this zero. Just to change the sign and put them minus 2 here and plus 3 here. All right. Then again we have to make this zero. All right. We have to make this zero. What we can do now? We can do R3 is equal to R3 plus 1 by 2 R2 like this. Alright. So we can do like this. Look out 1 4 minus 3 0 0 here. 16 becomes 16 60 minus 1. So 1 by 2 R2. This becomes 0 here. 1 by 2 of R2. 1 by 2 of R2 is 16 minus 1 by 2 here. And we go like 32 minus 1, 31 by 2. 31 by 2 like this. Alright. And this becomes we have 100 minus 210 3 minus 1 by 2 1. These are the three things. Alright. So this is the LU decomposition for us. This is L, this is U. Right? Is this true? Let's check. Let's let's ask this here. Like so we have a matrix A is equal to 1 comma 4 comma 3 no minus 3 comma minus 285 minus 2 comma wait a minute minus 2 comma 8 comma 5 comma 347 3 comma 4 comma 7. So we have this matrix. Alright, is a 3 by 3 matrix. What is the LU decomposition for this? Just saying here. L is 100. All right. L is 100 minus 210 minus 3 point minus point 5 1. 143 and 016 minus 1. All right. This is how you do LU decomposition. Are these suggestions of videos also? Let's see what is the videos.
In this video, we will determine the LU. In this video, we will determine the LU decomposition for this 3 by 3 matrix. And when we solve this problem, I will do it using a shortcut method. So let's get started. So first, I will draw a table. One side will be L, and the other would be U. With L, I'm going to have a 1 across, like this, and on the top right, we're going to have zeros. This is going to be L. These three numbers we need to determine. And now I'll do the U matrix. So I'm going to draw a box, and with the U matrix, it's going to be this, and this is going to be 0. So the first row won't change. So it's going to be 3, 0, 5. However, now I want a 0 to be here. In order to get this to be a 0, I need to modify this matrix. And when I do so, it's going to change this row, and it's also going to change this row. And I'll show you what I mean. And so a negative thirds times 3 plus 4 would give us 0. I will also need to do this for this number and this number. So negative 4 thirds times 0, negative 5 over 3, 17 of negative. However, I'll just write what we have so far. 1, negative 2, negative 3. But I need to modify this. You can say this is 0 times 1 R3. R3 is negative 2, so it remains negative 2. Lastly, negative 1/3 times 5
This
is
is the
negative
correct
5
way
over
to do
3
this one.
plus R3, which is negative 3. So negative 5 over 3 minus 3 is going to give us negative 14 over 3. And again, another rule. This is negative 1/3, so this right here becomes 1/3. And now we have one more. We need to make this to become 0. Same idea. And so if you want, you can pause the video here and try to get this to become 0. And so let's do that. So same idea. I can say that negative 2 over 5 R2 plus R3. This would give us the top row remains the same. I'm not changing that. The second row remains the same. I'm not changing that either. And the third row changes. So negative 2 over 5 R2. Negative 2 over 5 times 0. This right here is L. 1, 0, 0. 4 over 3, 1, 0. 1/3, 2/5, and 1. Let me write that down. So this right here is L. 1 over 5. This is U. It's 1 divided by 3 and 4 divided by 3. Hit enter. And our U was defined as matrix 3 by 3. We had 3, 0, 5, 0, negative 5, negative 17 over 3, 0, 0, negative 12 over 5. Hit enter. So now I will write A is equal to L times U, which is what we wrote. If I hit enter, I get 3, 0, 5, 4, negative 5, 1, 1, negative 2. I would get a completely different answer. And so this.
All right, this is how we do all right things. Thank you so much, guys, for watching the video. One few things are left here. We will discuss here only those things. Lower into lower triangular matrix. Lower triangular into lower triangle matrix is always lower triangular, right? And upper into upper is equal to upper triangular matrix. Right? A transpose is equal to minus A, then it's a skew symmetric matrix. Right? Orthogonal real simple matrix or a orthogonal real square matrix Q is equal to QT is equal to I. This is a orthogonal real square matrix, and is that columns and rows are orthogonal vectors. Columns and rows are orthogonal vectors. All right. This is how. This is why this we called it orthogonal matrix. Well, columns or rows are orthogonal matrix. A to power n is equal to a. So we call this matrix as idempotent. Idempotent matrix. Only one. So one more thing. Only identity matrix is is idempotent and invertible. No other matrix is both idempotent and invertible. Right? Only this. I square is equal to I. This is called idempotent, and I into I is also I. This is also idempotent. So this is the only matrix idempotent and invertible. Right? Thank you so much, guys, for watching the video, joining with us. Uh, Stop sharing and